We got data. We got one mission: to find a model that would fit our data really well. We cannot fail. So let us begin. So this is the code for this episode. This is a lot of code, but don't get discouraged. You know most of it by now. That is why we went step by step in this series, so that you can understand what we are doing while we are progressing to more complex code. You know already our objective function, the MSE, right, the mean squared error. I added here a plotting function that you also have seen multiple times by now. Maybe not as a function, but you definitely seen that we have used Plotly to do our interactive plots, right? But one thing is changing. We are not using our custom dataset and data loader anymore, but use a more popular solution, PyTorch Dataset and the PyTorch Data Loader class. In order to use PyTorch Data Loader class, we have to create a class, which I named Custom Dataset, that inherits from PyTorch Dataset class. As you can see here, we import the dataset class from torchutils.data. Additionally, we have to implement the init, the len, and the getItemDunder methods. The initialize method is quite simple, right? We are just setting x and y. This is our data. Len is also very easy. We just take the length of x, for example, because we check here that the length of x has to be equal to the length of y. And getItem is also not difficult. We are just accessing the elements of x and y with an index, right? And that is all, and just return x and the instance of x and y. Other than that, we created toy data. In this case, a polynomial function of third order, so a cubic function, right? This is that here with a little bit of noise. Then we put that data into a data frame class, but before we are plotting it, of course. Here, that is how our data looks like. And in this episode, we will change the game a little bit by having multiple candidates, so multiple models, and we want to find out which model is the best to fit our data. Our three candidates are a linear model, the code is living in this section, we have our quadratic model, and we got a cubic model. And in these Python files, linear.py, quadratic.py, and cubic.py, I have implemented the models as classes. So for example, here's the linear model. What we do is we set the weight, the bias for the linear model. We have a predict method that we use in order to predict, where we pass data as an input and give a prediction as an output. We also have a class method. We also have the computation of the gradient in here for the weight parameter and for the bias parameter. For the quadratic model, it's quite similar. We initialize it with the weights, with the bias. We have the prediction, the compute, they all look quite the same. Just the computation of the gradients and the prediction is just different, right? And the cubic model, we have it over here. Here again, it doesn't change very much. We just have an additional weight parameter. That is the weight parameter that sits in front of a cubic term. And we have predict, compute. And so this time we also need three gradient methods since we have three fitting parameters, right? If you vectorize that, you don't need three parameters, you can just use one. But in this case, I wanted to show you a different approach on how to do that, because before we have used vectorization, but you don't have to use it. But in general, if it's possible to vectorize the problem, you should do so, because the performance will be better, but it will be most often also a little bit more complicated on how to compute the gradients. But never mind. We will have multiple occasions in the future to demonstrate that on more complex models. Since our data was generated by cubic function, we can already guess who will be the winner, but this is just for educational purposes. In reality, you will only have your data, but no known function. You will have to create a few models and test them on the data in order to find out which is really the best, or whether one is even able to describe the data appropriately. It could be that all models suck on your data, right? Anyway, suppose we have only one training dataset and we train 3 models on that. How do we know which one is the best when we deal with a regression problem? Well, we would have a look at the loss of the last epoch, right? And check which one has reached the lowest value. That must be the winner. But we should be careful with this approach because it could be that one model performed randomly better at the training data or that we have tweaked it better on the training dataset. How can we be confident in our choice of one model over the other? Well, we can split our dataset into multiple parts. One training dataset, one validation dataset, and a test set. In our case, we are sampling randomly from that. We can see that here because we have loaded our data into a data frame, pandas data frame, and then what we use is the sample method on this data frame. The sample method will randomly sample values from this data frame, and the split method will divide them into divisions. So it will, for example, this split will divide our dataset into a split data frame and into a test data frame. And we use that split data frame, this is just an intermediate data frame, in order to generate our training data frame and our validation data frame. So, as I said, we are sampling randomly from the dataset and use 64% of the data for training. The training set looks like this. We use 60% for the validation dataset and 20% that will be used as a test dataset. So we are generating 10,000 instances. So 60,400 instances for the training dataset, 1,600 instances for the validation dataset, and 2,000 instances for the test dataset. You can see it here, right? When we split our data frame, or we are first sampling from it and then splitting it, we are splitting it in 80% of the portions of the whole data frame here. And the DF split will have 80% and DF test will have 20%. And then we are again doing the same split. So the training data has 80% of the split data frame length and the validations had 20% of that. Why did we choose such weird numbers? Well, usually when you have a look at the internet, we will find proposals like you choose a split like 99%, 0.5% and 0.5%, or 80%, 10% and 10%, or anything like that. Well, the actual answer is that there's no definite right or wrong in this question. There are a lot of research papers on this topic, and often they're also limited to specific areas. For example, there are a lot of research papers which focus only on linear regression models, but that finding doesn't apply automatically to other models. Essentially, in the end, a lot also depends on your data and on your model. In this case, I want to show you that we can still achieve our goal with an unconventional division to encourage you to experiment from time to time, because machine learning is a lot about experimenting with your data and with your model. Also, we are dealing with relative few instances. 10K is not very few, but also not too many. So we are using a large portion of the dataset for training, but we are also use some of that to validate our candidates. And in order to assess our model in the final test, we use relatively many instances in order to see how our model performs on the data that it has never seen before. Remember, our test set has 20% of the overall data. How does our training process looks like? Well, so for example, when we have a look at our first candidate, the linear model training, then we are having a data set, right, where we are copying over our training data frame, and we also have a validation data set, and we have our linear model. And what we do is we record in the history the loss for the training on the training data set and the validation loss. We will see in a second why this might be useful. And then we do it as always. As you already know, we are looping over the number of epochs, we are recording the loss, we are using the data loader here with a batch size of 128 and shuffle is set to false. In order to sample the data batch and the label batch, we do our prediction, we compute our loss, we are appending that loss to our loss recording, we are updating our weights and the bias, then we are appending the loss with the mean of all the losses during the iteration. And then what we also do, we do another loss recording, because now we are iterating over the validation data loader, And what we do is we make again our prediction, calculate the loss, append that, and calculate the mean of the loss, and append that to our history validation loss. This part is new for you, right? Because until now we only had one data set, so we only did this part. This is how you do the computation for the validation data loss. Once we are finished training, we use our trained models, and what you see here is that we are iterating over the data loader, and we are of course updating our model multiple times. And only after that we are evaluating the performance of the model in the validation dataset. This is very important. Since our candidates didn't see the instances of the validation dataset during training, we get an unbiased view on the performance of the models. We just have to be careful during splitting that the validation and test set are representative for the data population, but we already have seen that this is the case. We can use the validation performance in order to tune our models. Our metric here is to reach the lowest loss on the validation dataset while maintaining a low loss score on the training dataset as well. We will talk more about this when we have a look at the plots. Once we are finished with fine-tuning the hyperparameters, this is usually what we will do in order to improve our models, right? So once we are finished with fine-tuning the hyperparameters and have a look at the best scoring model on the validation dataset, we will make a choice. Once we have decided for a model, our decision will be fixed. We will use the winner candidate and evaluate its performance the final time on the test dataset, and have a look at the final loss value of that model on the test dataset. We will not fine-tune our model on the test set, since we want to see how well our model generalizes overall, right? Why do we do that? There is this famous anecdote of Fermi, Dyson and von Neumann, where von Neumann told Fermi once, "With 4 parameters I can fit an elephant, and with 5 I can make him wriggle his trunk." In machine learning we are dealing usually with tons of parameters that we can change during training, and so we can of course choose those weights in such a way that the loss becomes minimal on the training dataset. But if the loss degrades on the validation dataset, we will know that our model is overfitting. For example, this is how a model would look like if it would be overfitting the data, right? So the data are represented by the circles. We have on the x-axis one feature, on the y-axis we have our target label. We can see that our model is following our training dataset too closely. But the reverse can also happen. It can also happen that our model is performing bad on the training dataset and also on the validation dataset. The model is underfitting the data. The model is not complex enough in order to represent the complexity of the data. So for example here on this image you can see that this data is definitely not linear, but we are using a linear model in order to fit it. And of course a linear model cannot fit, for example, any polynomial to any degree, or an exponential or logarithm or a square root function. A linear model can only represent linear data, right? Okay, we talked enough about this. Let's have a look at the plots when we execute our code. So we have trained our model 10k epochs on a learning rate of 10 to the power minus 5. As you can see, our linear model is not able to capture the curvature, right? The curvature that is formed by the data. And when we have a look at the loss performance, it turns out that although our linear model is not the most appropriate choice, it doesn't perform that bad. As you can see, the loss got down by a lot, the training loss being at approximately 217 and the validation loss at approximately 230. The training loss is quite close to the validation loss. On the internet, when you Google about underfitting, you will see very often very extreme training and validation plots that clearly show that your model is underfitting the data. In this case, it is not that obvious, and this represents also reality. In reality, you most often do not see whether your model is underfitting or not. In this case, we can see it clearly from the plot, but when you deal with multi-dimensional models, it is not possible to make plots like this one, because it's just not possible to plot it in all dimensions. Because, for example, imagine you have 100 dimensions or 10 dimensions, 12 dimensions. you cannot plot that on a 2D surface. You have to rely completely on the data that we have here at hand. But we can also see that our linear model is underfitting when we have a relative comparison with the other candidates. So let's have a look at the quadratic model. This is the quadratic model. When we have a look at it, it is capturing the data better than the linear model. We are training with 10k epochs and a training loss of 10 to the power of -5. The training loss is at approximately 156 and the validation loss at 151. The training loss is again quite close to the validation loss, which is a good sign, and both losses are quite better than in the linear model case. And thus we can see that our quadratic model would be a better choice as a fit. That is because our quadratic model is capturing the complexity of the data better. Now let's turn to the winner. We can see that the cubic model is a really good fit on the data, and that it is able to capture the complexity of the data. Let's have a look at the loss performance to verify that. Well, we have trained this model, by the way, with 10k epochs and a training loss of 10 to the power of -6. The training loss is at approximately 99 and the validation loss at 103 or 104. The loss performance is the best from all three candidates, and this indicates to us that we should go for the cubic model and evaluate its performance on the test set. The spread in training loss value and validation loss is also the best out of those three, indicating that this model has the potential to generalize quite well. Let's verify that on the test dataset. So when we evaluate it on the test dataset with a script, then we can see that the cubic model reached a loss value of 102 on the test dataset. So sitting between training loss and validation loss. That is really good. So this model generalized indeed very well. So what I have presented you today was just one way of evaluating multiple models on the data. There are other techniques that can be employed, but most of them rely on the fact that you split your data into training, validation, test, or training and test set. There are techniques like cross-validation that allows to leave out the validation dataset, for example. We will learn more about this in future episodes. But for now, this is it. Thank you for watching. If you found this video insightful, then please like and subscribe, and we see each other the next time.